Other Ryan, back with you. So excited to be back and to continue with where Ryan A left off with regression. But we're going to take a bit of a different point of view. So let me share my screen and we'll go ahead and get started here. So day 7 of the intro course. So I'm impressed and proud of all of you who have hung with us for this time. We're going to keep on going here with more regression, which includes more models. Last night we got into linear regression, but we're gonna try some other model types for regression. We're also going to get into more features, which is sort of the machine learning type of terminology for what in statistics could be called an independent variable. So yesterday we did linear models with one independent variable. We can get into multiple independent variables, including some variables that are represented as strings that are in a certain order. And we'll have to convert those strings to numbers. A common thing that you'll do when you're working with machine learning projects in Python in the real world. And when we have so many different options for the features we could include in our models and the type of model that we could use, then we have to really understand, how do we choose the right model with the right features? We need to have a process to evaluate our models and choose the best one. And we'll talk about that. This concept of a model can overfit the data or underfit the data. And how do we find that Goldilocks sweet spot, right? We'll use some techniques and some terminology, which I'll explain as we go about splitting your data into training data and testing data, and then using some metrics such as mean absolute error we're going to use tonight. To help to evaluate our regression models. So more models, more features, more evaluation, but actually for tonight, less linear algebra. In fact, no linear algebra, just scikit-learn, which was introduced towards the end of last night. So, but the foundation that you had just in our 2-day crash course, you know what, that provides you with a great conceptual foundation and also an appreciation of what's really going on behind the scenes. So I'm really glad that you had that foundation. And now I'm glad that we can take a computational code-based approach to playing with some more data here. So let's dive in. We're going to look at diamond data. And I will plot just 10 data points. We're gonna use a artificially tiny data set so that we can see all the data, and that's gonna help us understand how these models will work. So here is the data. If we plot these 10 diamonds, their price on the y-axis, and then on the x-axis, their weight in carats. So that's the visualization. And if I take a look at the data frame, then I have here the carat, that weight there, and the price. And then there's this other column, which we'll come back to a little bit later tonight, about the cut of the diamond, whether it's merely fair or good, very good, or even premium or ideal. And so we might imagine that both the weight and the cut together might make a difference in the price of a diamond, right? So if somebody asked you, based on this data, how much you would expect a diamond to cost if it was 0.9 carats, what would you do here with these 10 data points? You don't have data for a 0.9 carat diamond, right? That's a gap in the data. But an approach that you might use is to simply say, well, I don't have a data point right here, but I'll just look at the 2 closest ones that I have. There's one here about 1 carat, and then another one over here, a little less than 0.8 carats. And so I'm going to estimate that here about $3,000, kind of splitting the difference. That would be my guess for 0.9 carats. if someone asked you, well, how much do you expect a diamond to cost if it weighs zero point 0.7 carats? Well, then instead of having no data points, all of a sudden now you have 2 data points, which seems similar. And again, you might say, okay, well, I'm going to take these 2, and I'm going to guess it's going to be roughly in the middle of those. And similarly, with a 1.2 carat diamond, larger diamond in our data set, we'll say, okay, we had 2 diamonds that look like they're the same weight, so I'm not exactly sure why they had different prices. Maybe it's some other factors like that cut. But if I didn't know anything else about it, just the weight, I'm going to guess it's probably about halfway between those 2 points, right? And this concept that you would just intuitively recreate informally, if you were given these 10 data points and some simple questions, that is a type of machine learning model that you've essentially rediscovered or re-implemented. And that is called the nearest neighbors model, or the K nearest neighbors model, where K equals 2, because we were looking at the 2 closest points. So we can implement that model quickly in code here. We're going to say that the features that we're using, we'll use a Python list to list out the features. And for now, we're just going to have the weight and carats. And then the target, what we're trying to predict here, is the price. So we can import from scikit-learn this K nearest neighbors model, a regressor model. And we'll talk more as we go. I'd like to actually start with some concrete examples and not belabor a lot of definitions up front. So we can take this nearest neighbors model and fit it to the data that we have. And now let's see if the predicted prices match the intuition of what we came up with when we looked at the visualization. So if I predict the price of a 0.7 carat diamond, then we see, okay, about 2,100. Let's scroll up here to the visualization and see that, okay, yep, that's what we would have expected. It's taking these 2 points, it's averaging them, it's coming up to about 2,100. Now let's take a look at this prediction for a price of a 0.9 carat diamond. That was one where we didn't have any data points nearby, and so we're going to average 2 that were farther away. So it's saying a little bit more than $3,000 here is the prediction for a diamond that weighs 0.9 carats. So taking a look at the visualization, if we scroll back up here, we say, yeah, that's about what we expected here, up in this neighborhood of about $3,000. And finally, not to belabor the point, but if we're going to predict this price of a 1.2 carat diamond, it says $4,400 was the model's estimate. And again, we see, okay, yeah, that's about splitting the difference of these 2 data points here. So that is the nearest neighbors model. This is how you would get predictions one at a time, passing them individually like this, but we can get multiple predictions at the same time. So if we wanted to get all 3 of those same predictions at the same time, we could just put them all in there in a list like so, and we get out those same predictions. We can do a whole bunch of predictions if we want to really understand across the entire range of that x-axis, what would this model predict? And this is going to help us to visualize how this model is working. It's kind of interesting. It's not quite the same as a linear regression model. So we can get predictions for, take little baby steps, each 1/100th of a carat, from 0.0 all the way to 1.3 carats. And here's one way we could do that, just with Python's built-in functions. The range doesn't take float values, it just takes integers. But if I go from 0 up to 130, and then I divide that by 100, then that's going to get me from 0.0 up to stopping right before 1.30, and taking those 1/100th of a carat steps. So So that's what I want to get the predictions for is this list of values. And I pass that into the model.predict function. I get those predictions, and now I can plot them. So let me explain here what we're doing, because there's a couple parts of this plot. So the first part, just the same as we did before, we're plotting these 10 dots that were our training data with carrots on the x-axis and price on the y-axis, like we did before. And the S is equals 50. That's just making the size a little bit bigger than the default, so we can help to see it. But now this plt.step, that's plotting these predictions that we calculated in the cell above here as a step function, to say, do a whole bunch of little dots and then connect the dots with these straight lines. And we see this is how this nearest neighbors model works, is that when we're near 2 points, it's going to split the difference. And when we get to a breaking point where we're like starting to get to where it shifts what the 2 closest points are, then all of a sudden we jump up. And now, like when we jump up to here, now this was no longer the second closest point. Instead, this one is. So that's why we jump up to this value. So just this simple intuitive type of model is a type of model that can't be expressed in a linear equation, and it can even model some nonlinear phenomenon, and can help us to understand what could be the relationship between the weight of a diamond and its price, even with just 10 data points here. Of course, we could use a linear regression model as well. Let's give that a try. So in this next cell of code, the first 2 lines of code here are different, but the rest of the cell is exactly the same of what we're doing before. So we're simply importing from scikit-learn this linear regression model objects, like we did last night's lesson, and then we're using exactly the same code to say, okay, the model, which is now a linear regression, we're going to fit that. We're going to use the features, just the carrots in this case, from the training data set to predict the target in the training data set, the price. We're going to generate predictions across every little point along that x-axis, and we're going to plot the dots, and then we're also going to plot the predictions. We'll give it a title of linear regression here, and here's what that model looks like. And so we see here that different pros and cons of these models, even though in this toy example with just the 10 data points, they're very similar, but yet you can see, okay, a linear regression could extrapolate better. So for example, on the high end, what if, say, I wanted to predict a diamond that was out here off the chart 2 carats? Well, my nearest neighbors model is just going to flatline out here, and it's going to continue to predict this value forever, right? The linear regression model would continue to extrapolate in a straight line. So the linear regression model intuitively would predict that a 2-carat diamond may be a higher value, a higher price than any data point than we've seen before. Whereas the nearest neighbor model cannot predict a higher value than the maximum that you've seen in the data set. So these are interesting things that you can learn about the model just by generating or making up a little bit of data, 10 data points in this example, and then visualizing it, inspecting the results, and thinking about what you see. So this potential strength of the extrapolation of the linear regression model could maybe be a weakness as well. Why? Well, maybe that extrapolation does not continue linearly. Maybe it does level off at some point, and it's linear in this region, but maybe it's supposed to level off at some point, or maybe it's supposed to continue up even faster than linear, exponentially. It's hard to know if we don't have that data, right? The other weakness you can see on this other end, the lower carat diamonds, because we don't have data in for very small diamonds that are less than 0.3 carats. We see here with this this y-intercept is about negative 1,000. So you're saying that, okay, if a diamond is 0.1 carat, then the jeweler is paying you to take the diamond instead of you paying the jeweler for that diamond. Well, that would be counterintuitive. But we can say, well, maybe this linear model is a pretty good model for the data within this range of the data, and we don't necessarily know when the data gets outside that range, right? There's a famous quote about models by a statistician, George Box. He said, all models are wrong, some are useful. So the idea here, and especially this is really a machine learning state of mind or point of view, is that we're not necessarily trying to uncover the true theoretical relationship between the weight of the diamond and the price. It's just like, hey, we're trying to create a predictive model that's going to help us make some accurate predictions. And if it's useful, great. If not, we'll tweak it to make it useful. But we don't necessarily worry that there may be some theoretically implausible results at the extremes. Hey, this model is still useful when it's used within these range of carats, right? We can get the equation for this line from that scikit-learn model. So if I run this line of code here, this is the coefficient, and here is the intercept, which as we saw visually here, was about negative 1,000. So that matches our intuition. And if we put this in equation form in the y equals mx plus b form, then we would say price is you take the number of carats and you multiply by over $4,500 per carat, and then you subtract out $1,000 for the y-intercept there, and that's the equation that best fits, again, this toy example of only 10 data points. And in this example, the straight line is a pretty good fit for these data points, right? Because even though these data points did come from a real data set, I cherry picked them for the purposes of this lecture. So it's a pretty good fit, but we can do even better. But maybe it would actually be too good. So let me show you a fit that could be too good for these 10 data points. This is called polynomial regression. So I'm pointing out here again in the comments, first few lines of code are different. The rest of the cell is the same. So we are fitting, instead of y equals mx plus b, we have an equation where y equals a coefficient multiplied by x to the 8th power plus another coefficient multiplied by x to the 7th power, and so on. This is going to give us a lot more flexibility in our model. And instead of me trying to explain it, let's just visualize it here. So if I run this cell of code here, we see, okay, now this function, this model fits the 10 data points here nearly perfectly. So this line was a pretty good fit, but we see some situations where a straight line, it's not going to be able to pick up both of these points that essentially are at the same x value. This data point here is a little bit low, so that the straight line's a pretty good fit. This one is even better for these 10 points. Fits the training data almost perfectly, but does not generalize to new data. So this would be an example where this model is not going to be useful at all on making predictions on how much a diamond that is 0.6 carats is going to cost. Or especially we're way off the chart here on the negative end with a 0.9 carat, and then way too expensive on a 1.1. Just for the fun of it, let's see the prediction from this model here. A 0.9 carat diamond, according to this model, would be negative $33,000. No, I don't think so. That prediction is absurd, of course. This model is too flexible. It overfits the training data, does not generalize well to unseen data. If you're curious, here are the polynomial coefficients. This model is overly complex. I haven't bothered to put it into an equation form, but this would be what you would multiply, y equals this big number times the number of carats to the 8th power, and so on. It's way too complex. So this model overfits. It's possible to also have a model that underfits. Let me show you an example here. This is called a dummy baseline. Opposite problem. So again, first 2 lines of code different, the rest of them the same. We're saying this model is always predicting the mean. So the predictions do not vary here. It's just taking the average diamond price across the 10 of them. So you're never going to have as absurd of a prediction, but this also is not useful either. It underfits the data. So now we've looked at 4 different models. Let me pause to take a breath here. And we want to know, how do we really evaluate these models and choose the best one? And you could say, well, whatever gives us the best fit, right? But we saw that, well, the best fit on the training data was this one, but this was actually the worst of the 4 that we've looked at for really the purpose, the usefulness of generalizing to unseen data. And so we're going to get into next how we can evaluate these 4 models and compare them in a fair way that is going to tell us that this one is the worst. If we do it right, we're going to say this is the worst, and then this is the next worst, and then these 2, the linear regression and the nearest neighbors model, are about the same. So I've already previewed how we're going to do that, but let me just take a break here at 25 minutes in. I'll check Slack and see any questions. Feel free to put them in Slack now as well if you'd like for me to address before we continue on. So Albert asked a great question. Do you have to view it to see the overfit, or are there other ways to check for it? In the real world, you're usually not going to view it. For the purposes of learning, it's very common to have these regression examples where you have a single variable on the x-axis, a single independent variable, and then the dependent variable on the y-axis, and you see the overfit visually, and it's really useful as sort of an aha moment. But imagine you add a second independent variable. All of a sudden, it quickly gets harder to visualize, right? Because you're either going to have to visualize it in 3D, but yet on a 2D computer screen, or you could have one of the variables be the hue, the color, and then another 2 variables on the X and Y axis. But if you add in even a single additional predictor, a single additional feature, independent variable, whatever terminology you want to use, it quickly becomes more difficult to visualize. And then once you get beyond 3 total variables, then it gets beyond our visual or cognitive perceptual abilities as humans to visualize that data. So the visual way, this is really just a learning tool to see it. But usually you will have to use math rather than visualization to see the overfit. So that's a great question. Other questions before we move on. All right. Well, don't hesitate to put it in Slack if you have other questions. Um, but what we're going to do to choose the best model and to avoid overfitting, we're going to use different data for training and testing. And this, in my opinion, is what separates a machine learning mindset from maybe an inferential statistics mindset. That maybe you're that instead of using all your data and fitting a simple model with a few predictors to all your data, and then looking at some goodness of fit metric, instead we're simply saying we're gonna hold out some data for testing, and we're not going to use that data for training. And if we're in this big data era where we have lots of data, then maybe that's okay. Maybe we're able to set aside some data and say we're not going to train on that. We're just going to save that for testing, and that's going to simulate future data. We don't know what sort of data we'll encounter in the future, but if we take some of the data from the past and set it aside, then that will simulate this idea of this unknown data that we hope that the model will generalize well to. I feel like I'm over-explaining it, or maybe in a confusing way, so let me get back to just running some of this code and demonstrating it again. So I have 10 more data points, and I will now plot both the original training data and the test data together on one plot. And so the training data remains the blue dots, and now these new 10 points, this test data, are the orange dots. So we see some differences here. We see where we were missing coverage before we had a gap in the training data at the 0.9 carats. Now we've got that covered in the testing data. So that could be interesting. It looks like we've kind of got an outlier here at 0.7 carats. That's okay. That's real world. In the real world, things aren't going to fit a straight line perfectly. So what we're going to do now, we're going to replicate this plot for each of the 4 models. It's basically going to be a mashup of this visualization within the visualizations that we've already produced. And then we're also going to calculate some metrics. This block of code, even though I've got some comments, this is a long block, the longest in the notebook, and don't get stressed out. I'm actually not going to explain it right now. Instead, I'd like to actually look at the output first, and then we can go back and walk through the code block. So now if I look at the nearest neighbors model again, the blue dots, again, were the training data points, and we're fitting the model to that. So this blue line is the nearest neighbor model, where we're looking at what are the 2 nearest neighbors and fitting the model to that. And then the orange dots are our testing data. So we're calculating a certain type of error, which is called mean absolute error, and calculating that both for the training data and the testing data. And we're actually interested in both. So as I put in the comments here, the mean absolute error for the training data is the average distance between the line and the blue dots. So if we take a look at this first blue dot here, I hope you see, it'll be hard to see the dot, but I try to make my mouse cursor bigger, so hopefully you can see it. There's really no error here on this dot. This is almost 0. But when we get into these dots here, there's some error here. These dots as well here. There's some error here. And so the idea here of mean absolute error is you're saying, what's the distance between this dot, and if I drew a straight line, if I drew a vertical line to see what's the distance between this dot and then the line for the model's predictions. So each of those represents the error or the residual. And if I take the absolute value of each of those errors, and then I take the mean of all those absolute values, then that's the mean absolute error for the training data. Now, the mean absolute error for the test data is very similar, but it is the average distance between the line and the orange dot. So we can see we've got a lot of error here on this outlier. We expected that. Some error here on this data point. Some others that seem to be some pretty good predictions. So we would expect intuitively that our test error is higher than our training error. Normally, real world, you will see that the test error is going to be higher than the training error, and that's okay. Ideally, you'd like to have them similar, but it's unusual in a real world situation if you'd actually have the test error lower. It's possible, but let's continue on and take a look now at the linear regression, and we see some similar numbers here where as we expected, these models, as we look at it visually, they seem to be pretty similar quality. And we see here that actually the linear regression is slightly better on both error metrics, slightly lower training error and slightly lower test error. Now here's where it gets interesting. This 8th degree polynomial. The test error is where we know that we can throw this out, because the training error for this model is the lowest, right? It's passing almost perfectly through these points. It has the lowest training error, less than $100 of error on these points, but yet almost $8,000 of average error on these test points. So this model does not generalize. And the machine learning mindset is to look at this test error as the way to select your model. So it's not about having some sort of rule of thumb that says, well, never use 8th degree polynomial models. They don't work. No, you may need a very flexible model to capture some complex or subtle relationships in your data. You may need a model that's much more complex than this 8th degree polynomial, such as a deep neural network. If you're dealing with high dimensional image data and you want to be able to find patterns in that complex data, you may need a model that's much more complex than this. So that the answer is not to say simple models good, flexible or complex models bad. No, the answer is to say hold out some of your data for testing only, not for training. Use some rigorous methodology because it's not quite as simple as the simplistic version that we're showing you here, but the fundamental concept is the same, that you don't train and test on the same data. You have different data for training and validating or testing your model. And sometimes a very simple model is going to be the best test error, and sometimes a very complex, flexible model is going to give you the lowest test error. It just depends on your problem. It depends on a lot of things. So let your empirical results of your properly validated test error be your guide. Enough about that point. The mean baseline we see here, the training and test error is very similar. They're both similarly bad. So it's not as bad of a model as this one, but it's still not nearly as good, of course, as a proper linear regression or nearest neighbors model. So we're talking about mean absolute error. It's not the metric, it's a metric that can be used to evaluate regression models. And it's one that I like because it's intuitive. It's saying, on average, how far off are you, the predicted values from the actual ones. So let's just step through this very briefly to make sure we understand how this works. And we'll look at manually calculating instead of using scikit-learn's function for mean absolute error, more manually calculating the mean absolute error for this baseline model. So in the baseline model, the predicted value is always the same thing. It's just the mean price, right? So just one simple line of code, I can say my predicted value is always that. I can take a look at predicted minus true for these 10 points. and here were the errors. At first, my predictions were too high, and that makes sense. So it's a positive value here. And then when you cross a certain point, all of a sudden the predictions were too low. So it makes sense that these numbers start to decrease and then even flip the sign, right? So these were the errors, how far off it was on each of these data points. Then we take the absolute value. So we're going to see the same 10 numbers again, except for they're all going to be positive now. And then if we take the mean, then we get the same result that we got before, where it was off about $1,300. Let's double check and see that that in fact was the case of the training error, the training error for this, this dummy baseline of just always predicting the mean value. So that's how the mean absolute error works. What if we just calculated mean error instead of mean absolute error? Then in this case, this number, if you're not familiar with scientific notation, it might be hard to understand this number, but this number is very, very close to zero. This is like the same as this number. It's zero within a little bit of non-zero way out here, about 13 decimal places in. So what's happening here, and this makes sense for this baseline, the positive and negative errors are canceling each other out. They're zeroing each other out. So that the mean error would not be a good error metric. But mean absolute error works. Other metrics like mean squared error, by squaring the errors, then they all become positive. So that works as well. Mean squared error is going to punish larger errors a bit more. And it also is what ordinary least squares is minimizing by default, is mean squared error. So conceptually, these are very similar. I like mean absolute error because it's just extra intuitive. But in practice, mean squared error might be slightly more common to use because it is what OLS is minimizing ordinary least squares. So now that we've covered the error metric, we've understood here by using training and testing data, and then comparing the test error, that we can identify to say the linear regression was the best model so far. Good thing we learned about it last night, right? It's a great model for regression. But we've been doing simple regression with a single variable, a single independent variable or predictor or feature. Again, different practitioners use different terminology. What if we wanted to use more features? For example, we have another feature here in our data set, this cut of the diamond. Well, if we try to use cut as is with scikit-learn, we get an error. So I'll just demonstrate this for the sake of seeing what could be a scary error message if you're not used to dealing with error messages like what is all this gibberish, right? Well, the key is down here at the end. This value error could not convert string to float, where it encountered this string ideal. And scikit-learn is saying, wait, this isn't a number. I expect numbers. I demand numbers, right? So we will have to deal with that. We'll do it in just a moment. Everything else was the same here in the code that we've been doing before, so it's not a difference in our code. The only difference here was that we added to our list of features that we said now we want to use caret and cut, and that's where scikit-learn threw up this error. Because cut, as we just mentioned, is a string, not a number. So let's convert this to a number. The fancy vocab term for a feature like cut is that it's ordinal, simply meaning that those values are in order. The cuts have a ranking where fair is the worst, and then it goes to good, then very good, premium, and then ideal. So we can replace those words, those strings, with numbers in order, the integers 1, 2, 3, 4, or 5. or really any integers that are in order like that. So let's go ahead and do that. I'll use there are multiple ways that we could do this. One way is to use Pandas map function, which if you're not familiar with that, you could Google Pandas map, or you could use in a notebook, you could use the help function that Aaron has demonstrated. And that's going to apply this dictionary to these cut values, and then we're going to say I'm actually going to replace it with the results here. So let me run this here, and now all of a sudden we see numbers instead of words, instead of strings. So now that's it. Now we can use cut. Let's actually try one more model type, a new model type with our new feature here. So we're going to say, okay, our features here are caret and cut. Our target still is price, and we're going to use a decision tree regressor. And then this line is the same that we've been using over and over again. We're going to fit that model. Okay, it worked. No scary messages about not recognizing the strings because we've got numbers here. So it worked. Now we're going to calculate the error again. This is the same block of code, so don't be overwhelmed. The same code that we've used earlier. We'll just throw this in a function called error because we'll use it several more times in these next 10, 15 minutes here together. So if you've read ahead in the comments, you see the train error is 0. The test error is higher than 0. So this model overfits. It's not quite as bad as that 8th degree polynomial, but it's still overfitting. And train error is 0. How would that happen? Well, I do like visualization, and so we're going to look at the tree. We're going to visualize it to try to understand it better. This does require a library that you may not have by default. So if you're on Google Colab, you can run this code block, which I've already done, so it's telling me that requirement's already satisfied. If you're on your local machine, then I'd recommend you use the Anaconda distribution of Python instead and use this command to install the required dependency. So sorry for that interlude. And now if I use these this short block of code here, this is going to visualize the decision tree. This could be overwhelming, and I'll be honest, looking at the time here, I'm a little bit nervous to explain this in the time allotted, but I'll do my best. And this notebook is here for you to dive in and to explore it on your own if you'd like as well. So this decision tree, which we've turned on its side here, it is splitting the data from the 10 data points, and it's splitting it up into smaller and smaller groups and trying to make different predictions for the different groups until it gets to what are called the leaves in the trees. So it's starting out saying that, okay, to start out, we have 10 samples, we have 10 data points, so that makes sense. If you had to predict one value for all 10 of them, it's going to predict 1640, which is actually not the mean of the data set. That's actually the median. So the mean is what would minimize MSE, mean squared error, but the median is what minimizes mean absolute error. And that's an interesting thing that I did not learn until I was putting together this lesson for you all and exploring it. And I think, again, this is a great way to learn, is just play with some small data sometimes, data that you can see. And then if you come across something counterintuitive, then explore and try to figure out why you're seeing that. So saying, okay, this is the value if you had to predict for all 10 samples, and here is the mean absolute error you would get with that. But we can do better than that. We can split the data into two groups based on whether the weight in carats is greater than or less than this point. If true, we go down this path. If false, we go down this path. So what this algorithm is doing is it is discovering for you these if-then rules, which you can imagine if you had a lot of patients, you could maybe inspect the data and try to figure out some of this for yourself and write it out as Python code, like if caret is less than or equal to 0.87, then we go down this path and we change some.
You froze for a second there, Ryan, but
Hey, am I back now?
you seem like you're back. Just
Okay. Are you seeing my screen again?
yep, all good.
Okay.
Blame
Sorry.
Comcast and carry on.
So I apologize for all this cryptic text. We won't have time to walk through all of it, but the main point to get here is that this decision tree is continuing to split until its individual predictions, where it's essentially just memorizing the training data. It's splitting it until you get down to sample sizes of 1. And so it's potentially again memorizing the noise in a data set, in the training data set, and not necessarily the true signal that might generalize to unseen data. So there's a parameter of decision tree, several different parameters, in fact, that can be used to prune the tree. So one of them is this minimum number of samples per leaf. And that it's fairly intuitive. It's saying don't keep on branching until you get to leaves that only have a single data point, because that might just be, really overfitting on the training data. So here we don't have a lot of data points to work with in this sort of artificial scenario. But let's say that the minimum number of samples per leaf, instead of being 1, is 2. So now when we run this again, the test error is even worse than it was before. It's telling us not that decision trees are bad, remember, but just that in this particular example, we've got only 10 data points. 10 data points is not going to be enough for this type of model. You're going to need to have a simpler model like a linear regression. But we can take a look at the visualization of the tree and see that, in fact, this one parameter, changing minimum samples per leaf to 2, it has now pruned the tree the way that we expected, so that it did not continue to split this group of 2 into 1 and 1, and this group of 2 into 1 and 1, and so on. It stopped here at groups of 2, and in some cases here, even groups of 3. And so that's a way to try to prune the tree to control overfitting. Since the decision trees didn't work out as well as we would have hoped, at least not on these severe limitation of 10 data points, let's return to linear regression, which was our best model so far. But this time, instead of using the single feature of caret, the weight, we'll use both features to do a multiple regression. We use the exact same code as before. We define that now that the features is both of them, and if we refit the linear regression, that is now a multiple regression with both features. Now we have the lowest test error so far, and we can get out the equation now, which is slightly more complicated because we have the 2 features. So what this is saying is, here's the coefficient for our first feature, which is carets. Here's the coefficient for the cut, and then here is the intercept. It makes sense that both of these coefficients are positive, because we would expect that the more the diamond weighs in carats, the higher the price is going to be. And the way that we set up the cut variable, when we encoded it as an ordinal integer, we did it in an ascending way, where 1 was the worst quality cut, all the way up to 5 was the highest quality cut. So we would expect that as that cut number goes up, that again, we would have a positive association with price, that higher, better cuts lead to a higher price. So it would be a red flag, a signal for us if we were seeing negative numbers in these coefficients. It means that either our domain intuition, our domain knowledge or expertise is incorrect, or we've done something incorrect in the modeling process. And I will tell you, in my real world experience in the insurance industry, working as a data scientist before Lambda School, I've experienced both. I've experienced times where we find a surprising insight that maybe the relationship between the predictor or the feature and the target is counterintuitive. But honestly, probably more often it's the other situation. It's that I screwed something up, or that maybe there's some omitted variable, some hidden confounder. And I apologize now, I brought up that notion without adequate time to explain it, but there's a lot of things that can go wrong in machine learning, and that is part of the challenge of it, but I think also the excitement of it. You're not going to get bored when there are so many things to debug, right? So, anyways, let's apply this model that we fit to predict the price of this 0.9 carat diamond with a very good cut, which corresponds to number 3 out of 5. So if we use this formula, we can use Python here as a calculator, and we can use this coefficient, multiply it by 0.9 carats. This coefficient, multiply it by the cut was 3 out of 5, and then the intercept, and we get out this prediction, which is what we had found before. This hasn't been changed radically by this slightly more sophisticated model, but we're still saying it's about $3,000 for this kind of diamond. And if we use, instead of this manual sort of equation, if we just use the dot predict method of the model object, then we get out essentially exactly the same value. Why is it not literally identical? It's because we rounded off these coefficients here. So this is essentially the same. If we want to do a sanity check, again, we're familiar enough with these 10 data points, but just humor me. There's no comparable diamond in the training data. Again, that was a gap. We didn't have anything that was 0.9, but the test data, as we saw, has 2 0.9 carat diamonds. One has a higher price, but a better cut. The other has a worse cut and also a lower price. So even though we didn't see anything that was exactly this weight and a cut of 3, having a predicted price in between those, that's plausible. That's a good little sanity check. Could we figure out this formula just by looking at the numbers? Well, if it was that simple regression, then sure. It's just 20 numbers, plot the data, draw a line through it. You don't need scikit-learn or any math to do that. But, it quickly becomes more complicated. Add just one more dimension, and it gets harder. We could use the linear algebra, but I would not be able to do it just by visually inspecting the points somehow, or looking at the table of numbers and somehow coming up with this equation. I couldn't do it. Maybe you could. So even though adding just one more dimension, we still only have 30 numbers to manually inspect, I would not be able to figure out that equation looking at 30 numbers. And 30 numbers, that's artificially small, of course. These 30 numbers come from a much bigger data set, which we'll use for your assignment in just a minute here. This is it's called the Diamonds data set. And so there are almost 54,000 rows in here, and not just 3 columns, but actually 10 columns in the full data set. So in total, you've got almost 500,000 numbers there. I would not want to look through all of those to search for patterns by hand. although it is interesting. Couldn't help but share this story with you if you are curious. Prior to the invention of Jupyter and scikit-learn, a Russian mathematician constructed a decision tree by hand, by interviewing some doctors and figuring out a simple decision tree that was a diagnostic test for medicine. So it can be done, but I'm sure glad that we have computers to help us along the way in the journey. So we'll hop into the assignment in just a moment here, but I will bounce over to Slack for questions. And then at the bottom of this notebook, what I'm calling recap with references, but it's actually maybe a bit of a misnomer because some of this terminology I did not really cover during the lesson. But that's somewhat by design. I wanted to provide the concrete examples for you first. And now some of these glossary terms, which come from Google's glossary, which I find is a helpful, concise resource for defining some of these terms. Now some of these definitions I think will make sense to you and maybe they wouldn't have up front. So I would say read through these when you have time. I've also highlighted from Wikipedia, tried to excerpt and bold some content that I think will explain what we're doing here and how the humble linear regression can even be considered to, yes, it's inferential statistics. Yes, it can be solved with linear algebra, but it also can be considered a type of machine learning. And we're going to continue on with machine learning tomorrow. And not do just regression, but classification. So this is a little bit of a preview for tomorrow as well. Have documentation for the model types that we used in scikit-learn, and even some free practical books that are going to give you hands-on code samples in Python to do some of this regression stuff with a variety of machine learning model types. But now let's go over to Slack for any quick questions, and then we'll hop into the assignment because we're about at time. Let's see. Britton says panic ensues.
Yeah, this is when your internet suffered.
Oh, okay. Yes, Britton, I was a little bit panicked as well, so I'm glad that was resolved quickly. Does it matter if the relative value or difference in impact of the ordinal rank variable is not just linear? Yes, absolutely. And there are all sorts of different ways of encoding categorical variables that first of all may or may not be ordered. There are many different ways with different pros and cons. We're going to explore some different ways to encode categoricals tomorrow in the machine learning lesson for classification. And some of this is a art versus a science. So I will tell you, Albert, there was a time when I wanted to find what is the right way to do this. And it really, the right way is whatever way gets you the lowest test error or validation error when you use proper validation methodology. And again, back to this idea that all models are wrong, but some are useful. So maybe even if the ordering is correct, maybe it's not a linear relationship, but you know what? By the way that we did it is probably going to get you close enough. But if it didn't, there are different ways that you could explore in your data and maybe try some different encodings. So great question. And that was my response was a long-winded way of sort of dodging it by design. I would say just try something and then you can kind of tweak forever and try different things and see if there's anything that can improve your model performance. Sometimes the hardest thing is deciding when is it done? When is good enough, right? I see another great question in here. Less error is better, but are you also looking for training error that is close to testing error? Yes, I think we'll talk a little bit more about it tomorrow, but I would encourage you, especially if you were to look at some of the resources that I've provided in here, when it gets into the free practical books, this chapter of the Python Data Science Handbook, and also this brand new book. It's just beta, the first 2 chapters, but I'm super excited about it because it's by former president of Kaggle, who was the top competitor 2 years in a row. And it's really this not theoretical machine learning knowledge, but applied practical knowledge, which is what hiring managers are looking for in industry when you're going to break in and get your first job as a data scientist after going through Lambda School's full 30-week program. So it's too much. Again, I apologize for the dodge to really fully explain all this in the 1 minute or negative 2 minutes that we have allotted here now. But you're asking absolutely the right question, and I would encourage you to refer to these resources as well as come back tomorrow and tune in, and hopefully we'll get to that a little bit more. So you think, Aaron, it would be a good time to flip over to the assignment?
And the only thing I was going to say is absolutely. There have been great questions and conversation throughout the lecture, and keep that up. You can keep doing that as you work on the assignments. And yeah, as Ryan said, there's a lot here. You're not going to absorb it all tonight, but it's great to ask questions and just keep exploring and trying things. And that's what the homework is for.
Yeah, absolutely. So do the students have the link to this assignment? Has that been shared with them yet?
I don't think so. So go ahead and just paste that in the Slack.
Okay. So I will paste this in here, assignment. And so I'm gonna have kind of three problems, but there's some challenging ones. So the third one is a stretch one. Don't be discouraged. But the first one, experiment with the nearest neighbor. You're going to go back to these 10 data points, which I've provided for you. So execute this cell, but now train a nearest neighbor regression model with number of neighbors equals 1 instead of 2, and use both features. Calculate the mean absolute error for both the training data and on the test data. What I would say is absolutely do refer back to the lecture notebook, which I believe has been shared with you. If not, wouldn't hurt to paste it quickly in the chat. Do refer back to that, but I would encourage you, if possible, to not copy paste. Even if it seems tedious, type it out again. As I mentioned when I was teaching the inferential statistics lesson, that will help you to internalize the concepts in a way that simply copying and pasting won't. So see what happens when you tweak that parameter, compare it to the similar model that we did in the lesson, see what happens. Now, after that, you're gonna run this code to load a whole lot more data. Now we're not talking about 10 data points. We're talking about training data that has almost 30,000 rows and test data with almost 10,000 rows. So it is in the full diamonds data set, all the diamonds that have a price less than $5,000. Then please train a linear regression model that uses both the caret and cut features. Calculate the error, specifically the mean absolute error, for both training and test. Use this model to make a prediction on what a half caret diamond with a very good cut would be. And then now here's what I think is the fun part. You choose what features and model type to use. See if you can get a better mean absolute error on your test set than your model that you did in the last question number 2. So you can explore different things. There's a link to the documentation that's going to explain some of these other features in the data set that we didn't cover in the lecture. So yeah, do your best on this. We'll see how it goes. But I think that this could be kind of fun because it's in a way open-ended, but yet there is criteria for success. It's, can you get a better test set error than you did before here in question number 2? If we're choosing different features, aren't we answering a very different question? It depends on why you are doing the regression. If you are trying to gain insights about certain relationship between some independent variables and a dependent variable, then yes, it's a totally different question. If you're trying to say, give me the best diamond price predictor that I can get, then no, it's not a very different question. It's the same question, and you're using whatever means at your disposal, any features, any model type, any model parameters to try to get the best answer to that question of of predict me the price of a diamond that you might be using. Even though this is a contrived data set and a contrived example, you could see how this would apply to business use cases where you're predicting the value or the price of something as a buyer or seller of some good or service. There is a very interesting research paper that I could send you about these sort of two philosophies. But yeah, what for the purpose of this assignment, please adopt the mindset of you're trying to create the best diamond price predictor, and really success is evaluated based on your out of sample predictive accuracy. So I apologize, I took too long to introduce that assignment, cut into your time. So I'd like to give you maximum time to work on this. So I'd say dive in if you haven't already.
Yep. Thanks everybody. Get to work, and in a bit less than an hour, meet with the PMs. Thanks.
Thanks.